Hello everyone, let us continue our discussion. We are in week 9 and this is our lecture 2. Now in this week our main aim is to study the deflection of beams, right? And in fact we have already derived the expression of bending stress distribution across the section, and we have also studied shear stress distribution. And if you recall those expressions, sigma by y is equal to m by I is equal to minus E by R. Right. And shear stress distribution tau is equal to VQ by IB. We have also derived EI d2 u dx2 is equal to minus mx. This is the bending moment at the rate x. Now this x normally we take from the left end of the structure. So if you recall, we considered simply supported beam with UDL over the entire span. Now this is omega acting uniformly over the entire span, and therefore we can consider any section within the span, and if we find out mx, just by varying x we can find out bending moment at every section within the span. Now, if we double integrate this equation, first we get du dx, that is the slope, and then next, if we again integrate, we get u of x. And this model is called Euler-Bernoulli beam theory. Right. Now, not always we have beams which are under UDL over the entire span. For example, if you have, say, a beam, same simply supported beam, and we have a point load, then a patch load, then for this, the question arises where we should take the section. Is it here or there or here? And we can have different combinations of load, just like you can see here we have a point load and patch load. Similarly, we can have a beam with general loading. Now the question that we are trying to address in today's lecture is how to solve a beam which is having a general loading, and for that we are going to apply Macaulay's method. Now what is so special about this method? First, it offers the equation of the deflected profile of a beam under general loading. It is particularly useful if you have multiple point load and UDL. Now for that we need to first define Macaulay's bracket. So if we have x, we write with Macaulay's bracket as you can see on your screen. Now it means the value is x when x is greater than equal to 0, and it is 0 when x is less than 0. Similarly, if we have x minus a within Macaulay bracket, then its value is x minus a when x is greater than equal to a, and it is equal to 0 if x is less than. Now imagine we have x minus a Macaulay bracket to the power n, and we differentiate this with respect to x. Then we get n x minus a within Macaulay bracket to the power n minus 1. Just like we have a function x minus a. Similarly, if we have integral x minus a within Macaulay bracket to the power n d of x, we have x minus a within Macaulay bracket to the power n plus 1 divided by n. So you can see the differential of the function or the integral of the function is as good as we have x minus a to the power n, and the same way we do it for this function, we also apply with Macaulay bracket. The only thing is on the right hand side also we have Macaulay bracket. Now the main feature is within this bracket, if we have negative, obviously the value will 0. That means that expression will vanish if we have negative within this Macaulay bracket. Now let us see how we can use this and solve the bending problem if we have a general type of loading. So if we have, say, a simply supported beam, and we have two loads at the quarter points. So the length of the beam is L and flexural rigidity is EI. Now, before we solve the deflected profile, let us first find out the reactions. So for that, first we apply equilibrium of forces along vertical direction, and that gives us RA plus RB is equal to the loads acting at the top. So it is P plus P, so we have 2P. Similarly, we apply moment equilibrium about the point A, and it gives RB times L is equal to P times L by 4 plus P times 3L by 4. So effectively we have RB is equal to P. So RA is also equal to P. That means we have two reactions, P and P. Now, when we apply Macaulay's method, so we consider a section covering all the loads, right? So we have two loads, then we get X here. So for this section, Mx is equal to Ra, which is P. So we have P times X, but we apply Macaulay's bracket here. Minus, we have this load, first load P times X minus L by 4 within Macaulay's bracket, minus P times X minus 3L by 4 within Macaulay's bracket. Now we can apply the expression for moment at a section X. So it is EI d2u dx2 is equal to minus mx. That means minus p times x in Macaulay's bracket plus p times x minus L by 4 plus p times x minus 3L by 4. So if we integrate this expression, we have EI du dx is equal to minus p x square by 2 plus p times x minus L by 4 whole square divided by 2 plus p times x minus 3L by 4 whole square divided by 2 plus we'll have a constant C1. Then again if we integrate, we have EI u of x is equal to minus p times x cube divided by 6 plus p times x minus L by 4 to the power 3 divided by 6 plus p times x minus 3L by 4 to the power 3 divided by 6 plus C1x plus C2. Now the only task is to apply boundary conditions. So if we see the boundary conditions, we have u0 is equal to 0 and u of L is equal to 0. That means at the two extreme ends, we have no deflection. Now if we consider the first boundary condition, and then if we put this in the expression of the deflected profile, we can easily see on the right hand side, we have p times x cube by 6. So x is 0, first term is 0. Second term, we have within Macaulay's bracket x minus L by 4. So the moment is x is equal to 0. Within Macaulay's bracket, we have negative, so it vanishes. And then third term, x minus 3L by 4. Again, if you put x equal to 0, this term also vanishes. And C1x, because x equal to 0, this term also is equal to 0. So we are left with C2 is equal to 0. Right. So we get the first condition C2 equal to 0. Now for the second boundary condition, again, left hand side is 0. On the right hand side, we have first term p L cube divided by 6 plus p L minus L by 4. So this is 3L by 4 whole cube divided by 6 plus p times, we have L minus 3L by 4. So this is L by 4 whole cube divided by 6 plus C1L. So let us solve this expression and then we will get C1. Right. So let us try that. So C1L is equal to PL cube divided by 6 minus, we have 3L by 4 whole cube. So we have PL cube times 27 divided by 6 times 64 minus, we have PL cube divided by 6 times 64. So C1 is equal to PL square divided by 6. So within bracket we have 1 minus 27 divided by 64 minus 1 by 64. So we have PL square divided by 6, and here we have 64 minus 27 minus 1 divided by 60. So in the numerator we have 36, and we can simplify this. So we have C1 is equal to 3PL square divided by, right? Okay. So now we get the expression for deflected profile. So let us write down the expression for deflected profile, and then our next task will be to find out the central deflection of the beam, and we will also check the expression for theta at the two ends. So this is C1. Now the deflected profile is EI U of x, which is equal to minus P x cube divided by 6 plus P x minus L by 4 whole cube divided by 6 plus P times x minus 3L by 4 whole cube divided by 6 plus C1, that is 3PL square divided by 32 times we have x. Now, if we find out central deflection, for that we have to put x equal to L by 2 in this expression. So we have 1 by EI. Then the first term is minus P by 6 times L by 2 to the power 3. So PL cube divided by 6 into 8, that is 48. Plus the next term we have P L by 2 minus L by 4. So that is L by 2. So PL cube divided by, again we have 6 times 64. Then the third term, that is P times, we have L by 2 minus 3L by 4, which is negative. So P by 6 times 0. Then the last term we have, we can actually remove this term. So the last term we have 3PL square times L by 2. So 3PL cube divided by 64. Now, if we simplify this expression, we have 1 by EI, and then we take PL cube divided by 48 outside. So we have minus 1. Actually, we can take 16 common. So PL cube by 16. Within bracket, we have 1 by 3 then, plus 1 by 24, plus 3 by 4. Now, if you simplify this expression, we'll get the value of delta C, and that is equal to 11 PL cube divided by 384 EI. So that is the central deflection of the beam under 2-point loads at the water points. Right. Now our next task is to find out the slope at the two ends, and for that we use the expression as you can see on your screen. The only thing is we have to modify, so the value of C1 is equal to 3PL square divided by 32. Right. Okay. So for the first slope at the end A, the x is 0, right? So in this expression, if you put x equal to 0, we'll get the first slope, right? Let us do that. Okay. So now theta A is equal to 1 by EI, and on the right hand side we have to put x equal to 0. So first term minus P by 2 times 0 plus we have P by 2 within bracket again x minus L by 4, so x equal to 0, so that is negative. So again we have 0 here, plus third term again we have 0 because we have negative within the Macaulay's bracket, plus 3p L square divided by 32. That means theta A is equal to 3p L square divided by 32 EI. Now the remaining task is to find out the slope at the extreme end, that is x equal to L. Now for that, again in this expression we have to put x equal to L, and let us see what we get. So theta B is equal to 1 by EI, and then within bracket we have minus PL square by 2 plus P L minus L by 4, so 3L by 4 square, that means 9L square divided by 32, plus we have P by 2 and then L minus 3L by 4, so that is L by 4, so we have L square divided by 16 plus 3P L square divided by 32. Right. Okay. So if you simplify this expression, we will get the expression of theta B. Right. So let us see what is the value of theta B. So we have 1 by EI and PL square divided by 32. If we take it outside the bracket, then we have minus 16 plus 9 plus 1 plus 3. So effectively we have 9 plus 1 plus 3, that is 13, plus 13 minus 16, so minus 3 PL square divided by 32 EI. So you can see the value of theta A and theta B, they are equal, but the direction is opposite, because if we draw the deflected profile, you can see that for theta A we have this way. So the value of theta A is here, but for theta B value is same, but the direction is opposite, and that's the reason we have a negative sign here. Okay, so we have obtained central deflection and the slope at the two ends. With this example, you can see how we apply Macaulay's bracket for this two different point loads at quarter points, right? So let us continue our discussion and let us see for a different loading pattern how we can apply Macaulay's bracket and solve the problem. So this is example 2. Again, in this case, we have a simply supported beam and we have a point load along with a patch load, right? And this is 10 kilonewton per meter, and here we have 20 kilonewton. So the length of the beam is given . So the total length is 6 meters, right? Okay. Again, let us first solve the beam, find out the reactions. For that, again, we apply force equilibrium and we get RA plus RB is equal to 20 plus 10 kilonewton per meter over a length of 2. So 10 into 2, 20. So altogether we have 40. Then we apply moment equilibrium, MA. So we get RB times 6 is equal to 20 times 2 plus 10 times 2, that is the total load, times the lever arm, which is 5. So it is 140. That means RB is equal to 140 divided by 6. So we have 70 divided by 3 kilometer. So RA is equal to 40 minus 70 by 3. So we have 50 by 3 kilonewton. So we have two loads at the ends. So this is RA, which is equal to 50 by 3. And at the other end, we have RB, which is equal to 70 by 3. Right? Okay. So next is we will find out the moment at a section X from the left hand, right? And what we'll do, we'll consider both the loads and we'll take the section at a distance X from the left hand so that it covers the complete domain, right? So for that, what we do, we consider a section here. And for that section, mx is equal to RA times x minus we have 20 times x minus 2 minus we have 10 times x minus 4 square by 2. Okay. So now EI d2u dx2 is equal to minus m. So we have minus RA times x plus 20 times x minus 2 plus 10 by 2, which is 5 times x minus 4 whole square. Okay, so if we integrate this expression, we have ei du dx is equal to minus Ra times x square by 2 plus 20 times x minus 2 whole square by 2 plus 5 times x minus 4 to the power 3 by 3 plus there will be a constant C1. Then again, if we integrate ei, u of x will be equal to minus Ra times x to the power 3 divided by 6 plus 20 times x minus 2 to the power 3 divided by 6 plus 5 times x minus 4 to the power 4 divided by 12 plus C1x plus C2. We also have to apply Macaulay's bracket here, so C1x. Now we have boundary conditions. So for that, displacement at 0 is 0. Now in the last expression, if we put x equal to 0, obviously all the terms on the right hand side will be 0. First term x cubed by 6, because x is 0, it is 0. Second term x minus 2, the moment we put x equal to 0 within Macaulay's bracket we have negative, that means it is equal to 0. Third term again x minus 4, so x equal to 0 means within bracket we have minus 4, and then again within Macaulay's bracket we have x, so it means C2 is equal to 0. Similarly, displacement at L is equal to 0. So for that we have 0 is equal to minus Ra times L cube divided by 6 plus 20 times L minus 2, actually L equal to 6, so we can put that value, so 6 cube. 6 minus 2 is 4, 4 cube divided by 6 plus 5 times we have 6 minus 4, that is 2 to the power 4 divided by 12 plus we have C1 times x equal to 6. So L here is 6. Right. Okay. So here we can simplify this. So we have 36. So here we have 10.67 and then we have 5 into 1.33, and in place of Ra we can write 50 by 3. So 50 by 3 into 36, which is 600, then 20 into 10.67, which is equal to 213.4, and then we have 6.65. Now if you solve this, you get C1 is equal to 63.33. So now we have the equation of the deflected profile, and we can find out the central deformation. So we'll do that in a minute, and we'll also check the slope at the ends. So we have EI u of x is equal to minus RA x cube by 6 plus 20 times x minus 2 whole cube divided by 6 plus 5 times x minus 4 whole cube divided by 12 plus, in place of C1 we have 63.33 x and C2 is equal to 0, right? Okay, so we have solved the complete problem. The only thing is we have to find out the central deflection and the slopes. That we'll do in a minute. Okay, so delta C is equal to 1 by EI. Within bracket we have minus RA, which is 50 divided by 3, that is 16.67 times, for L we have 3. So (27) divided by 6, that means 4.5, plus we have 20 divided by 6, that means 3.33 times x equal to 3, so 3 minus 2, 1, so we have 1 here, plus 5 times x equal to 3, so 3 minus 4 minus 1, so that means this term will be 0. Then the last term we have 63.33 times 3. That means if we solve this expression, we have (176.65) divided by EI. Okay. Now let us find out the slope at the two ends. So we have delta C is equal to 176.65 divided by EI. Okay, so let us find out slope at x equal to 0 and x equal to L. Now, theta A is equal to 1 by EI, and then we have to put x equal to 0, so all the terms will be 0 except the last term, that is 63.33. Right, so we get theta A is equal to 63.33 divided by EI. Now let us also verify the slope at the other end, and for that we have to put x equal to 6. So theta B is equal to 1 by EI. Then within bracket we have minus 50 by 3, which is 16.67, times we have x equal to 6, so that means 36 by 2. Then we have 20 by 2, that is 10, and then we have within bracket 6 minus 2, that is 4, so 4 square 16, plus we have 5 by 3, that is 1.67, times 6 minus 4, so 2. So 2 cube is 8 plus 63 point. So we have 1 by EI. Within bracket, we have minus 300.06 plus 160 plus 13.36 plus 63 point. So this is equal to minus 63.37 divided by EI. So that completes the exercise. So we have theta B is equal to minus 63.37 divided by EI. Right. So we have the complete shape of the deformed beam, and we have also find out the central deformation, and we have also found out the slopes at the two ends. And here also you can see the slope at the end B is having a negative sign. That means it is in the opposite direction. So these two examples clearly show us how to apply Macaulay's method when we have a beam with general loading. We have a combination of point load or patch load, or maybe a combination of different point loads. We can easily adopt this method using Macaulay's bracket, and we can solve for the complete beam. Right. So we'll continue with this example. Let us close here, go through these examples, and just see whether you can follow all the steps. If you have any difficulty, do let us know, and then we will clear your doubts. Thank you very much.